one final innovation to the uh, material, to the process means that process is called like a material. And next one, how we choose why did choose the choose this those materials. A lot of materials is there, like air. Air also is one of the material, because air particles also having the positive atoms and also equal to the negative atoms. So air also is a best conductor, and copper, gold, silver, etc., etc., and human body, hair samples, these kind of things is also act like as a material. So we need to make a one material, means that material we need to find that conducting process, right? So that conduct process only is called like a materialization progress. Okay. And then next one. Yes. So antennas. So a lot of types of antennas.
Vinod
Yes,
sir,
yes, ma'am.
1 minute. I can hear some other stuff voice also.
Okay.
Okay, sir. Now we can continue. Actually, there is a delay. Is there?
Yeah, okay, ma'am.
Okay, sir. You can continue.
Yeah, okay. Next, we need to see like a antenna process. So, lot of types of antennas is there, but today we are particularly seeing USB devices antennas. So, USB devices antennas means it's a compact and portable antennas. So, we need to fetch one portable antenna, means that kind of antenna is a completely a miniaturized and also has a high power handling capacity with low cost. So, this kind of antenna is called like a miniaturized antenna, as well as it is called like a low profile antennas. There are two types of antennas only comes under in this terms. One is microstrip antenna, that is called like MSA antennas. This antennas is completely based on radiating layer and on perfect equal grounding method. So this kind of antenna is called like a MSA antennas. And second one is planar inverted F antennas, that means a PAFA antennas. This kind of antennas, one F size resonator we are introduced in the mid of the transmission, means that transmission is progressed one. So this is called like a PIFA antenna. Okay. And the comparative. So comparative, we need to know about the difference between these two things, because these two things is only is the printed circuit board antennas. Apart from that, balanced antennas are the elemental structure antenna, but these two things are the coating, that means printed antennas. So that's why we need to know about the difference between these two things. First one, pattern. So radiation pattern. Radiation pattern means if I give us some input from that from a radiating layer, means that layer will proposed to will produce the electromagnetic progress due to in the process of surrounding magnetic fields, right? So that kind of process is called like a patternized characteristics. So it is produced like a eight shape pattern. So eight shape pattern means it's a bidirectional pattern. That means in the forward direction as well as in a reverse direction. So this is called like a directional beam antenna. Any direction we can find any direction. We need to frame a 30-degree beam, means we need to give a 30-degree beam, or else a 60-degree or 45-degree or the 90-degree, whatever beam you can generate any of degree angle of beam, means that kind of antenna is called like a MSA antennas. Or otherwise, we need to propose a single unitary progress. That means only 180-degree only is in a process communication, means that kind of pattern is called like a omnidirectional pattern antenna. So it covers only one direction, but microstrip patch antenna covers around the 360-degree. So that is the difference. And second one, gain. So gain means the total power from initial end to, that means the 0 to a maximum end, that means the lambda cases. From 0 to lambda, how much of power will transfer, that kind of process is called like a gain. So that gain is as in a high, always is in a high, because MSPA is a purely for air particle structure or oriented communication. So it transmit a signal from lighting wave equal to the lighting wave speed. But in PIFA is a different part. So it's a different part means, so it is produced like a some resonance conditions. So the resonance conditions means each path, that means each produces, that means a lambda means lambda by 4, lambda by 2, and lambda by 3 by 4 lambda, and then lambda. So this kind of four stages there. So each case having a moderated process. So that moderated gain is called like a in PIFA process, but is a standardized one from starting to ending is the same power will transmit in the without loss means, that is called like a high gain process. So MSA is always high gain process because of its purely air transmission progress. And PAFA is a different part. So this is a resonator oriented condition means it is produced like a structural path progress. So this gain is on a moderated one. And third one, modeling and fabrications, both are is an easiest one. Both modeling and fabrication, both is easiest one. So that is not a different cases. And third one, application oriented means then in MSPA, they are using a wide range of applications like mobile phones, satellites, etc., etc. But in PAFA, it's a limited one. It is used for only as an internal devices alone, not on an external purpose. But MSA is an external purpose also we need to use. But PAFA is an only for internal purposes. That means compact insert modems and mobile phones. That means mobile phones means before 4G mobile phones. So this kind of internal progresses is called like a PIFA antenna. And merits and demerits. So this is the important case for the exact difference between MSA and PIFA. Okay. So and microstrip patch antenna means it's a low cost. That all this is also is on a low cost, but the size is as on a moderated one for MSA. But in PAFA is the smallest size. It's a fixed one. Like the size is 4 mm cross 8 mm, or else for 8 mm cross 16 mm. That's a standardized size. That kind of size is called like a PAFA. But MSA is in a based on the frequency, the size will be is in a different one. And also it's easy to integrate because this is purely based on line model characteristics. That means a transmission line model process. So transmission line means that the impedance is perfectly matched with initialized impedance. That means characteristics impedance is matched with as an initial impedance. So it is easy to install for any devices. That is not a problem. But in PAFA means is a little bit lag is there because that impedance is completely different. So that's why we can't match. We can't easily match with the impedance factor. So that is the merits and demerits problem. But in the problems, MSA also having the filtering structure and PAFA also having the filtering structure, but it is produced like a uh, not a slanting edge and narrow edge process. This is not a constrained path, so we can produce any of bands with any of process. But in PAFA is the constrained path, so we can produce a narrow band characteristics only. So this is the comparison of that two types of antennas, right? Okay. So next design method. So we enter into a design method process. So design method means we are having a lot of design method is that around 4 types of design methods is there, but as an mainly concentrate on a design method means that is called like a finite element method. So the word itself gives the meaning finite. So we need to find the all elements value in predefined calculation. After that we are doing one modeling means that model will produce the exact frequency result. So that is the FEM method. So FEM method is purely based on matrix theory. So matrix theory, whether it's produced like a 3x3 matrix or 6x6 matrix, whatever it's based on that frequency and based on the scale allocation, it is produced like a matrix. So based on that matrix itself, we can find the finite Fourier transformation progress. So that finite Fourier transformation process is the exact results of operating frequency in that particular antenna. So this is the design method of progress. Okay, and the flow. So this is the design flow. So we need to do one design means in predefinedly. First thing is we need to find an applications. What is your application? What is the exact applications you are doing? So first thing, you need to identify the application process. After that is a frequency selection, because each and every application having the multiple frequency sets. Okay, like a mobile phone means we are having a 1G, 2G, 3G, 4G. Now it's a 5G. So all the five generations are provides a different set of frequencies, right? So we need to find the frequency set first initially. So that is a second case. And third one, we do on a simulation. So that simulation is purely based on a transmission line model process or else a resonator model process. Whatever it's, you can select either which one is a convenient for you. So that is the thing. But in the industrial orientation process, mostly as a transmission line model is a preferable one. A resonator model is preferable for only as an meta component analysis alone. So that is the things we need to find the simulation process. And the third condition is we need to verify the parameters. So what are the parameters is that? What is mean by parameters? So each and every element, each and every electronics elements having a different set of values. So that values are equal to the some predefined calculation. That predefined calculation set is called like a parameters. In our RF and microwave process, we are having a different types of parameters: S parameter, Y parameter, Z parameter, ABCD parameter, then invert Z parameter. So we are having different types of parameters. But in all the parameters, S parameter is the most valid performance process, because S parameter is directly proportional. That means S matrix is directly proportional to the time. So directly proportional to the time means we need to find all the sets in this in a direct manner, because F is inversely proportional to time. So that concept is the main concept for parameter verification. And so after that, we have to fabricate and then test using a vector network analyzing process. So this is the simple structure diagram to choose what is the design process of antenna progress. And next, detailed flow chart. So this detailed flow chart will provide exact operations what we do in the simulation. After that simulations, what with the analysis. So all the cases is comes under into this kind of flow chart. Okay, so in before itself we saw first step is an application, after that is a frequency selection, and third one is a material selections. Material selection means we need to find the frequency first thing. So each and every frequency having a different molecule atom function. That means current process, current property. Okay, based on that current property, we need to select the materials. In a high frequency means it is having the low permittivity condition. So we have to select a high permittivity material. And the low frequency means it is having the high current density. So we need to choose the less permittivity of material. So based on that, that is inversely proportional. Material permittivity also is an inversely proportional to the frequency, because material permittivity is directly proportional to the distance traveled by the signal. So that means as a wavelength of lambda. So that's why material selections also is comes under into a different part. So after selecting the material, we enter into a design method. So in this design method, we are having a two types of model. One is a transmission line model, and second one is a resonator model. Line model is directly proportional to the time process, because it's entirely based on a lambda condition. Lambda means distance between source to destination. So that is a lambda. So that condition. So we need to find all the elements in the easiest manner. But in the resonator conditions means we need to frame. First of all, we need to find the wavelength. That means distance between the source and designation. After that only we proceed the process, means that is called like a resonator model. So we reassign the process. That means we reassign the frequency with a perfect path. So based on that path thickness, we need to find the length of the path. After that only we do a analysis process. So this is the some lengthiest process. So this kind of process only used for metadata analysis alone. But in the transmission line model is the easiest one, and also we need to find all the elements in the direct manner. So it is the preferable condition one in a research method. Okay, so after that you make it as a mathematical analysis. Mathematical analysis means in a TL model and resonator model, both are having a different set of formulas. A resonator model having a four set of formulas, and TL model having a 7 set of formulas. So based on that formula, we need to find the mathematical expression first of all. After that, we do a design. So we do the modeling. So modeling is based on completely as a three-dimensional structure. So 3D oriented printer. So we need to make the outlayer of that printing method. So after that, after making the simulation process, we go for an analysis conditions, whether the analysis is satisfied or not. So satisfied means what is the exact frequency we have to we select in before condition. That means initial mathematical condition, the same operating frequency is occurred in that simulation means it is a verified one, and also it's a good process of a good process transmission. Otherwise, we need to again change over to the mathematical expression. Again, we do the design process and go for a analysis. So this three circling setup is called like a optimization technique. So that means optic antenna electrical system analysis method. So optic antenna electrical system analysis method means it's a 21 method is that this all the 21 method is based on a three elements alone. What does the three elements mean? It is the most impact element of an electrical and electronics, both cases. Without these three elements, we can't make any circuits. So that is the most important one. It is none other than is a resistor, inductor, and capacitor. That means RLC. So RLC is the basic component for all the electronic circuits, as well antenna also having this three performance alone. So based on that one, we need to analyze the S parameter conditions. So after verify the S parameter conditions, you need to go for a modeling technique. Sorry, modeling. Since this modeling is purely based on as a light etching method. That means etching process method. Etching process method means in a VLSI, we need to frame a one PCB board means we follow a seven formation technique. So based on that seven formation technique, we make the fabrications. After that, we do on a testing process. So this is a complete flow chart to provide so to do a simulation of a single antenna process. And next one, S parameters. So in before we are having we heard about the scattering parameters. So what are the parameters in that S matrix means? We are having around seven parameters. So first one is a losses. So in a transmission line having four different kind of losses. One is return loss, reflection loss, a transmission that means a reflection loss, and the insertion loss, and then absorption loss. We are having four different losses, but in antenna circuits, in an antenna element having only two losses. Consideration of two losses only is an antenna process. One is a return loss, and second one is insertion loss. In the simulating model, return loss only we are doing as a simulating model, but in an insertion loss is purely based on a theoretical process alone. And next one, once we find the return loss means based on that return loss, we need to find the reflection coefficient value, because how much of signals will reflect in that particular path. So we need to find that one as an initial condition. So that is called like a reflection coefficient. So after getting that reflection coefficient, we need to make a VSWR process, because reflection coefficient is equal to modulus of 1 plus 1 VSWR plus minus 1 divided by VSWR plus 1. So this is the formation. So we need to rearrange that formation means VSWR is equal to 1 plus tau divided by 1 minus tau. So based on that formula, we get the VSWR level. That means voltage standing wave ratio. How much of the timing process will occur in that particular application in that constant zero axis. So that is called like a VSWR. So that value in the theoretical value of that VSWR is purely is a 0 to 1 only. So but in that simulation and then practical analysis, we can't get on a 0 to 1 process. So we need to extend the case. So extend that case is 0 to 3. So that is the maximum case. But in at present in a 5G means it's a 0 to 2 only. So this is a required thing. So we need to first we need to identify what is the required thing. So this is the required thing. And third one is an impedance. Once we achieve the VSWR means automatically we find the impedance plot. Impedance plot one, that is not a difficult one. I think we are all doing some Smith chart calculation. The same Smith chart only here also we are using for identify the impedance factors. So after getting that impedance, we need to find the efficiency factor, because antenna having two different types of efficiency. One is physical body antenna efficiency, and second one is a radiation efficiency. Both efficiency we need to find. So simple structure, from our antenna theory, from our source of antenna theory, gain is directly proportional to the particular direction process. That means in that particular beam, how much of power will transmit from source to destination. That total progress is called like a gain, and the total distance of that source to destination is called like a particular direction. So designation direction is called like a directivity. So that both gain and directivity is always directly proportional. So we need to remove the directional constant, means we introduce the some directional constant. So that constant is called like a neta. Neta is an efficiency factor. So neta is equal to gain divided by directivity into 100%, means we achieve the physical body efficiency of the particular antenna. And after that, we find the radiation pattern. So based on that radiation patterns, we need to provide the PQRS point analysis. Based on that PQRS point analysis, we find the radiation efficiency of that antenna. And third and fourth important point is a power. How much of power will receive, how much of power receive an antenna, and how much of power radiated from that antenna. So we need to find that one also, because if we give that we get power from source to antenna, means we need some path. So that path is called like a connectors. So that connector is called like a SMA connector, single mode access connector. So we need insert that connector into our physical body antenna, means that insertion also provides some losses. So that kind of losses is called like a insertion loss. So based on that insertion loss, we need to find the accepted power of the antenna, and then radiated power of the antenna. And a last and final is an SR, specific absorption ratio. That is as purely depend on the human safety manner. That means not only for a human, this is the earth safety method. So all the antenna comes under below 1 watt per kg, means that means the radiation emission of that antenna comes under below 1 watt per kg, means that antenna only is the safest antenna. Otherwise, the antenna is an unsafe antenna. So we need to find SAR value also. So that is also one important case. So now we are doing one simple structure antenna. So this is a simple structure. This antenna is particularly used for V2X communication. V2X communication means vehicle to anything communication. It is purely used on autonomous car function. This is autonomous car function. This frequency band is comes under in the terms of 5G mid-band application. The fifth generation mid-band characteristics. Mid-band characteristics means 1 to 7 gigahertz. So that 1 to 7 gigahertz is called like a mid-band characteristics. In that mid-band, we are having a four different sets. The first set is called like a sub 6 gigahertz. It is starts from 3.4 to 3.6 gigahertz. It's purely used for 5G mobile communication. And second one is a Vivo 5G, or else a sub 7 gigahertz. This is also extended version of that mobile phone communication. It starts from a 4.2 gigahertz to 4.75 gigahertz. So that is the Vivo 5G approximation. And third one is a Wi-Fi 6 and Wi-Fi 6E. So that is a new set of frequencies. So that frequencies comes under in the form of 5 gigahertz to 5.8 gigahertz. So this kind of ranges Wi-Fi 6 and Wi-Fi 6E. And fourth one is a V2X process. This is 5.85 to 5.95 gigahertz, just 100 megahertz of bandwidth alone. This is purely used for autonomous car function. So this antenna only now we are doing in a simulation process. Okay. So now we are enter into the simulation process. Just wait. So we are doing the simulation in this Answers 2021 version. So Answers is the most predictable software. This one software is enough to do on all electrical, mechanical, and electromechanical process. Everything we are done in the single software. and the efficiency factor of that software is very high compared to all other electromagnetic softwares. So we are doing some design process in this software alone. Okay, so this is the initial condition. So we are having a three different axial pattern. So this is called like a symbol of antenna. I think we are all see like a symbol of antenna. Symbol of antenna is represent the three-dimensional factor. It's covered entire 360-degree process. Each degree is in a 90-degree and adjacent degree of 30 degrees, 30-degree process. So we are adding the all the components means it is provide like a 360-degree process. So that is called like a antenna deviation process. So now we are doing one design for the simple structure, and this software having three different window. So this first initial window is called like a project manager window. This window having the entire details about that particular project, and this is called like a systematical window. This systematical window is having entire details of the design process, and third one is as in a design process. Okay, we're having a two set of materials is there, sorry, structures is there. One is a three-dimensional structures and another one is a two-dimensional structure. So three-dimensional structure is completely it's called like a solid elements, and two-dimensional structure is called like a coating elements, solid elements and coating elements. And before going to do antenna design, first thing, so we need to find an application. So first case of application, here we are taking as a V2X communication application. That V2X communication means it is a 5.85 gigahertz to 5.95 gigahertz. That center frequency is in a 5.9 gigahertz. So based on that 5.9 gigahertz, we are taking as a solution frequency. So we do a calculation used on that transmission line model formula means we are having the exact dimension factor. So that dimension, I think already we are doing the dimension factor. So directly we enter into the design process now. Okay. So first thing, that means in a design process, first one is we need to make a substrate, right? So we have to do as a 3D. So we do one 3D box. So this 3D model we are the base substrate material. So here we are having solids. So it is produces solids. Here we are having a vacuum process. So we need to modify the material. So we need to change the material into substrate. So substrate, we need to identify the material factor. We are having a library. In that library having all the material factors. So if you want, you need to add a new material calculations also. Here we are doing the FR4 material because it's a high frequency. Sorry, it's a low frequency because 1 to 7 GHz only. So 1 to 7 GHz means it's a low frequency set. So I'm using high frequency permittivity. High frequency permittivity means FR4 having a moderated one. So it is in a 4.4 now. So I have to choose an FR4 epoxy here. So after finding that FR4 FXC here, we have to need an access position from substrate and ground. Both are as always is an originated condition. So we have to choose a 0, 0, 0. And after that, we need to find the length and the width of the substrate. So x-axis is provide a width of the length of the substrate. So length is in a 21 mm because I taking in a square. So 21 and 21. So 21 mm means it's a 2.1 centimeter. That means exactly is in a 2 centimeter antenna. So 2 centimeter means below 1 inch, below 1 inch antenna only. I'll take as in a 1.6 as in a base material thickness. So now I have to frame this one, right? So this is the base material process. So this is a three-dimensional material. So we are doing a three-dimensional material one. So after making a three-dimensional material, we need to coating the elements. So we need to coat the element means I hope now is fully visible, right? Yes. So next we need to code the copper element. So we need to code the copper elements means we have to add a sheets. So we have to take a some sheet function here. So this is a rectangle one. So first thing is in a ground. So I'll take us in a G and E ground. So this is also always is an originator. So 0 comma 0 comma 0. So axis and a width length 21. Y is in a width, that is also 21. So I'll apply 21 and 21. And after making that one, so now it's a visible one, right? In bottom only we are quoting a copper elements. In top is in a fully open. That's all. Okay. So we need to assign the electrical property. That means conductor property. So we go for boundary conditions. So assign the perfect E conditions here. So this perfectly produce the exact copper conductivity material is now. And next one, we need to frame the radiating layer. Top layer is called like a radiating layer, or as well as it is called like a patch. Okay, so I have to make a patch now. So this is the I have to take another one rectangle. So that rectangle is called like a patch. So we need to modify the patch here. So we enter into the dimension part. So this patch dimension is different from our original dimensions. It's based on that fringing effect condition. So based on the fringing effect condition, this length and width value is only 11.45 alone. Okay, so 11.45. So that's why. So 11 point, sorry, 4.8 comma a 4.8 comma as in a 1.6, and here is an 11.45 value. So based on that 11.45 and 11.45, just apply and okay. So now we have to place one rectangle into mid of the radiating. So this is comes under into top of the radiating layer. In bottom is called like a ground. So this is also, this is called like a ground, and this is called like a top. Okay, so in between of distance is 1.6 1.6 mm is in a thickness value. Next thing, we need to find the resistive path. Okay, so resistive path means it's the input path. So that is also comes under into one rectangle formation. So we need to draw one rectangle here. So assign that rectangle into as in a feed. Okay, I'll take as a feed here. So again, we enter into the rate rectangle. Based on the transmission line model calculations, we have a exact value. So it's 11, 6.7 comma 0 comma 1.6. This is the length of the feed is an 8 point, is an width of the feed is 1.6, and length of the feed is an 8.5. So I take as an 8.5. So apply and okay. So we assign the input path also. So in this path is overlapping to the patch, right? So path and patches is a overlapping condition. So we need to avoid that overlapping, then only the perfect transmission is occur. So we need to avoid the overlapping means we insert this feed line into this radiating layer. So we need to insert the feed line means we additionally add one capacitor. That means one slot. That slot is called like a capacitor. So again, we have to draw another one rectangle here. So that I can go for create rectangle option. In that create rectangle, we need to find the exact calculation method. So it is called like a 4.8 comma 1.6, and sorry, is an 8.9 comma 4.5 4.8 comma 1.6. Okay, and next this is thickness value is in a 3.2, and the length value is a 3.7. 3.7 means it's an average factor value. So total value is an 8.6. So subtract from 4.8 means you are getting someone. So let us select a patch and this rectangle one and subtract both of. So you have to subtract means it is produced as a some filtering path. So this is called like a capacitive path. So we are assigning some capacitive path here. So after that we merged from patch to feed. So we merge the unite the patch to feed means it's a single component access. So again, we assign the boundary conditions. Okay. Ma'am, is my window is visible, ma'am? Madeline, ma'am?
Yes, sir, it's visible.
Okay, ma'am.
I can see the slide number, I think 12, simulation by using ANSYS 21.
Oh, okay, okay, ma'am.
Okay,
So you
sir?
want you want to see the design, right?
Yes, sir.
Oh, okay, ma'am. Now it's visible, ma'am. Design window.
Now it's visible.
Okay. Okay. Once again, I do all the things is in. It's not a matter. Okay, this is the first initial design window process. Sorry for the interruption because again. So I hope now you are all visible my design screen, right?
Yes, sir, it's visible.
Okay, ma'am. So first thing, initially we need to make a substrate. So initially I do. So initially you enter into an HFSS window. So this window having a three different path. So the first one is, so this is the design property window. This is a property dimension property window, and third one is in a project manager window. So first case we do a material. So this is a three-dimensional box. So we make a one square box. So so modify that box name into as a substrate. Okay. Next we have to select the material. So we need to go for a library allocations. So based on that library, I have to select the material is FR4 epoxy. This is a flame retardant fourth order substrate. So this is called like a glass and clay method. So we can't break easily. So that's why I had to choose an FR4 epoxy method here. So I had to get FR4 epoxy, and after that we enter into analyzing process. So this analyzing is always substrate and ground is always is an originated one. So 0 comma 0 comma 0, and next one is 21 and 21, and this is a 1.6. This all the calculation is based on that transmission line model calculation. So based on that calculations, we get a dimensions value. Okay, so now we have to make a one FR4 board. So after that we need to paste the coating material, that means a copper material. We need to coat a copper. So I had to select a 2D elements here. So I had to draw any one of 2D elements. So change that element into first initially is in a ground. So I'll make it as in a ground here. So after that go for create rectangle. So and before itself I tell substrate, and then ground is always is an originated one. So 0 comma 0 comma 0 is there, and next 21 and 21. So this dimension value is purely based on the um, insufficient fringing effect value. This is the insufficient fringing effect value. After that, in a radiating layer, it is completely based on that fringing effect value. Okay. So again, we have to draw one rectangle. So this rectangle, we need to change the name into a patch. Okay. So this is a patch. So we need to find this one. So this is based on the fringing effect. This length and width value is in a 11.45. So totally is in a 21. So we need to place that 11.45 in the mid of the 21 means, so we can find the difference. So the difference value is around a 9.6. So 9.6 means each side we are having an equal dimension value. So divided by 2 means we are getting a 4.8. So we need to make the process. So 4.8 comma 4.8 comma 1.6, because we need to make a top of the radiating layer, and this is a 11.45, and this is also 11.45. That's all. Okay, so now we get the top of the radiating layer. So we assign the condition, boundary condition. This is a perfect E. Perfect E means perfect conductor material. And second one is we need to place the resistive path. So resistive path means that is called like a feed line path. So we need to find the feed line path. So I have to change this one is in a feed line. Okay, so now this is on a feed line. So this feed line length is based on the calculation. It is around 1.6 is in a width, and then 8.5 is in a length. So based on that one, we need to find the mid value. So according the total 21 means we need to find the mid value is in a 1.6. So after that 21 divided by 2. So 21 divided by 2 means it is in a 10.5. So 10.5 and minus 0.8, because 1.6 is in a base width value. That width value also we need to mid, so we have to subtract from that one also. So like LG, that means the ground is ground length divided by 2 minus feed width length divided by 2. So ground length is a 21 divided by 2 means is a 10.5 minus is in a 1.6 divided by 2 means is in a zero point 0.8. So exactly we got a 9.7. So 9.7 comma 0 comma 1.6. Next this thickness value is in a 1.6, and then the length value is in a 8.5. Okay, so now that resistive path is overlap with radiating layer. Resistive path is overlap with radiating layer. So we can't make a impedance matching. So we now we do as an impedance matching means additionally we insert on capacitor means this resistive line is inserted to the radiating layer. So next one we need to put a one slot from that radiating layer. The radiating layer we need to put on slot. So we enter into that slot function. So this is the slot function. So the slot is 8.9 comma 4.8 comma 1.6. So we need to make a as per the calculation. And next thing here we got a 3.2, and this is one is a 3.7. That's it. Okay, now apply and okay. Now we are producing someone. So we subtract from this rectangle to our patch, initialized patch. So select a patch and then rectangle and right click on it. Go for edit. In that edit we are having a boolean operation, and that boolean operation we are having subtract. So you subtract from patch to this rectangle one. So it is in a merged path. So we have to merge the path from feed line to path. So we have to select both things, again go for edit and then boolean unite. Now it is provide a single impedance matching structure. That's it. Okay, so now we are assigning some input power. So we provide a input power means we need to place a port, right? So that port is called like a SMA connector. So SMA connector also here we are in that form of symbol characteristics only. So we had to select a rectangle. So we converted this one into as a port, right? Port. Before that one, we need to assign patch also as a boundary condition. So that boundary condition is perfect. Okay, so perfect E. So we need to place this port into this in this edge, right? This starting edge of the resistive path. So we have to select that one. So what is the initialized condition? Is an 9.7 comma 0 comma 0, and we need to change the axis also, because here we need a power axis is in a Y only. So we need to alternate the axis. Just wait, it will take a little bit of time due to server error. So wait here. So software taking some little bit of error. So I had to show the results today, and tomorrow we are doing the same design once again. Okay. So now I had to share some results. So now I share a results. So tomorrow I'll show the exact details. So this is the results. So this red line is shows that simulated value, and this dotted line is in a measured value. Okay, so measured value means we are analyzing the after fabrication process. So that is a measured value, and the peak gain of this antenna is in a 4.7 dB, 4.75 dB is in a gain, and then the power is radiated power is 28.5201 dBm. So it is converted into watt means it is approximately 0.78 watt. But in input power is at 29.99 means it is a 0 point converted dBm to watt conversion. You have to use the dBm to watt conversion mean it is a 0.94 watt. So approximately we got a 0.02 watt is a loss. Okay, so that is a power loss. So efficiency of that particular antenna is a 71.13 percentage efficiency. Generally in a patch antenna, we need to achieve more than a 60 percentage mean that is enough case. This antenna is having around a 71.13 percentage. So intensity, that is a power loss. 23.81 percentage is then a loss, power loss. That means insertion loss of the particular antenna. Okay, this everything is comes under into that plot method. But unfortunately today the server is disconnected, so that is a problem. So that's why I had to show the images. So this is purely based on that circular path, that means circularly polarized antenna, because each and every communications we need a 360-degree over communication. So that's why we have to choose the circularly polarization process. Okay, so I have to show the same design into tomorrow also. So don't worry, I'll do a same design as tomorrow. So if you have any doubts means now you can ask, I'm ready to clarify that one.
Students, if you have any doubt, you can ask sir. Sir is an RF and microwave engineer, antenna engineer, sorry, RF and antenna engineer working in Wilma Communication. So all these topics comes in Unit 3, microstrip antenna. And what are the simulation tools used comes under Unit 5. So SAR will be simultaneously covering Unit 3 and the software tools, which comes in Unit 5. If you have any queries, you can ask sir. And I have posted one feedback link in the chat box. Everyone should fill that. Vinod sir, we can wind up this session today.
Yeah, okay, ma'am.
Thank you, Vinod sir, for the wonderful session. Thank you very much.
Yeah, sure. Thank you, guys. Tomorrow we'll see the design process. Thank you.
Sir, you can leave the meeting
Yeah, sure, ma'am.
because I will take another 5 to 10 minutes to end up.
Yeah, okay.
Thank you very much, sir.
Thank you.
Students, I request everyone to fill that feedback form. And this microstrip antenna comes in Unit 3, last topic. And what are the simulation? What are the software tools used in antenna design? It comes under 5th unit. Okay. So the industry person will be teaching all these software tools, and uh, remaining part of the 5th unit will be taught by another one resource person. Okay. So those who are interested in doing, those who are interested in RF and microwave communication, and if you are interested in doing projects, your final year projects in antenna topics, this software tools, HFSS, will be very useful for you. So few students are sending message in the chat box that you are unable to submit the assignment from yesterday onwards. Yesterday was the due date. Due date is over. Then how will you be able to submit? You have the schedule with you. You have to plan accordingly. Okay, today one more day I will give. Those who have not submitted the assignment, you submit it by today itself. Okay. Someone reply in the chat box. One more day I will give to submit the assignment. Today I will enable that. So today everyone have to submit. Tomorrow onwards I won't give permission to submit the assignment. So follow the schedule what is given in the college. Okay. I will enable that. Only 78 students have submitted the feedback link. 300 students have attended this session. I want all the students to submit the feedback form. Only 90 responses I have received. Only 398 students have submitted the assignment. So one more day I will give. So I have changed the cutoff date to 14th. Students, you can submit now. Those who have not submitted the assignment, you can submit it. See, those who have not submitted, you check whether you are able to submit it now and reply in the chat box. I have changed the date of submission to 14. Check whether you are able to submit the assignment. Those who have submitted now the assignment, you reply in the chat box that I have submitted the assignment to just now, like that you reply. Because I have posted the feedback link also, I'm getting confused what you have submitted. Others can leave the meeting now. Those who have submitted the assignment now, reply in the chat box. Just I want to know whether you are able to submit or not. The others, you can leave the meeting. Yes, okay. Okay, I'm going to end the meeting. So those who have not submitted the assignment, submit it by today. Okay, okay. Register number 270, I read the message. You can leave.